This is our Aspen flowsheet, which shows a process design for the production of three main olefins: ethylene, propylene, and butene. This process consists of two main sections. On the left on the flowsheet is the STM, which stands for Syngas to methanol, and on the right is the MTO, which stands for methanol-to-olefins. Three thermodynamic models were used: NRTLRK, SRK, and STEAM MBS. NRTLRK, which stands for non-random to liquid, is commonly used for aqueous organic systems, which is suitable in our case because of the presence of water in the methanol production system. Another reason why we use this method was because it can describe vapor-liquid and liquid-liquid equilibrium systems. In comparison, the SRK, which stands for Suave-Redlich-Kwong method, is suitable for non-polar or mildly polar mixtures, and therefore it is usually used for the processes that involve hydrocarbons, water, and air, such as in the STM system. It is also suitable for the high temperature and pressure conditions used in the STM reactions. When using the SRK method, STEAM MBS is selected as the free water method, as the MBS steam table provides a greater accuracy, and the SRK method is designed to work with it.
The STM process, Syngas to methanol, consists of two reactors, a flash unit, and two coolers. The reactor type R-stoic was selected for both STM and MTO methanol-to-olefin reactions. R-stoic, compared to other models such as R-batch and R-CSDR, can be used when the reaction kinetics are unknown, but the stoichiometry and extent or conversion of reaction are known, such as in this case. For both STM and MTO, we were able to find and use fractional conversions from literature. Due to the low conversion of methanol achieved from the one reactor originally proposed, a second reactor was used. This method of using two consecutive reactors has been adapted also by Howder-Topsoe. The same operating conditions, so pressure 55 bar and a temperature of 530 Kelvin, were used in both reactors. As a result, methanol production was achieved with a conversion of 6.3% for the first reactor, STM1, and 11.3% from the second, STM2. This is equivalent to an overall single-pass conversion of 17.6%. The reaction of syngas to methanol is exothermic, which means that a considerable amount of heat is released as the reaction proceeds. Hence, the effluent stream from the first reactor was decided to be cooled down before being sent to the second. In line with Le Chatelier's principle, the forward reaction is favoured, and therefore a high conversion was achieved.
The effluent stream from the second reactor was cooled down to 35 degrees before being introduced into a flash. The main goal in this step was to separate any unreacted syngas present from the methanol produced.
90% of the syngas mixture was recycled back into the system in order to increase methanol conversion in the two reactors, whereas the remaining 10% was purged as waste.
The feed stream of the STM process is green syngas, which is provided at an operating pressure of 55 bar and a temperature of 530 Kelvin. We decided not to change the pressure nor the temperature of the feed. The stoichiometric number of the syngas was calculated to be 2.1, which means no additional adjustments are required. Any value higher than this indicates that there is too much carbon dioxide, meaning the stream requires purification. A molar flow of 99,023 tons per year of syngas was used, which resulted in the production of 80,000 tons per year of methanol, with a purity of 78.7%. We decided that the conditions of the methanol stream were suitable for olefin production, and therefore we used it as the feed for the MTO reaction.
Energy consumption and generation was evaluated using the energy analysis function, which is useful to identify potential energy savings. To save energy, several design choices were made. For example, the first MTO distillation column split, known as the ethane, between ethane light key and propylene heavy key was easy due to a high boiling point difference and relative volatility between keys. This led to a decreased reflux ratio and lower reboiler and condenser duties. Another choice was to not remove water in a column before the MTO reaction.
The main olefin we wanted to produce was ethylene, and based on literature we found that in order to have a higher conversion of ethylene, the MTO1 reactor should run at an operating pressure of 2 bar and temperature of 540 degrees. There are the reactions that take place inside the MTO reactor. We found fractional conversion values from literature. However, this did not work for our system, therefore we made the following assumptions. The conversion of methanol to light olefin is a highly exothermic reaction. Therefore, reactor MTO1 is cooled down in the cooler COOL3 before being introduced to a separation system. The effluent stream from the MTO1 reactor has a small amount of carbon dioxide and a large amount of water. Therefore, it was decided that only dehydration is required, and this was achieved using flash drums. As expected, the top stream of this unit contains all the light olefins, and the water was successfully separated in the bottom stream with a purity of 99%. However, the top gas stream of the flash 2 still has a considerable amount of water, 21%. Therefore, a second flash drum was used for further separation. In flash 3, water was separated with a purity of 99.7%.
Olefin separation occurs at high pressure, which is why the top stream of flash 3 was compressed to 20 bar before being introduced to a series of 6 DSTWU columns. This model was chosen because it allows the identification of minimum reflux ratio. Also, at this stage of our project, using RAFRAG is not ideal as it uses shorthand calculation and it is less rigorous. The first column uses the Demethanizer, where methane, ethane, ethylene were separated from the top, whereas propane, propylene, and heavier olefins were separated from the bottom. A reflux ratio of 1.5 was used in this column. However, we found that the bottom stream still had 51.7% of ethylene. Therefore, we decided to further separate it in another column, the Demethanizer 2, which operates at 10 bar with a reflux ratio of 2. The distillate product of this column was a mixture of ethylene and ethane, which was combined with the feed of the C2 split column. The third column is called the Demethanizer, and it operates with a reflux ratio of 1. In this column, methane is specified as the light key, and ethylene is specified as the heavy key. The feed of this column was cooled to 20 degrees to avoid the vaporization of methane. This resulted in the distillate product being a mixture of methane and hydrogen, and therefore it was taken as a waste stream. The bottom product was a mixture of ethane and ethylene, which was further separated in the column C2 split. This column operates at 10 bar with a reflux ratio of 2. In this column, ethylene was specified as the light key and was obtained as the distillate product with a purity of 98.9%. Next is the Depropanizer, which operates at 18 bars and uses a reflux ratio of 2. In this column, propylene was specified as the light key and was separated as the distillate product with a purity of 99.4%. The bottom stream of this column was composed of heavier olefins, where butane was the most abundant one. Therefore, we decided to separate this as the last olefin, and we obtained it with a purity of 99.9% by specifying it as the light key in the C4 column.
We can conclude that with the help of literature, market review and the block flow diagram, we were able to make a process flow sheet on Aspen without any errors. This simulation has also helped us understand the sustainability and the economic aspects of this process.